Hello, everyone. I hope you're all safe and sound during this pandemic, and I am looking forward to meet you personally in the next event. My name is Teo Aruera, and I'm a biological science graduate student in the Federal University of Rio de Janeiro, where I am associated to the Integrated Laboratory of Aquatic Ecology. Today, I'll present the results from my research in this work called Flood Pulse Dynamics Drive Benthic Macroinvertebrates Community Functional Structure in an Amazonian Stream. The Amazon rainforest is widely referred as the most biodiverse ecosystem in the world. It is located in the largest and most complex river system connecting to the coast, and it is the largest riverine system in terms of water discharge. In the lower reach of the Amazonian basin, we find the largest floodplain on the earth. It is under the influence of the flood pulse regime, which is the major force controlling biota in river floodplain systems, where matter and energy lateral exchanges between river channel and floodplain are crucial to biota. We can understand floodplains as areas that are periodically inundated by lateral overflow from lakes and or rivers by direct precipitation or groundwater. These changes in the water level because of the flood pulse lead to physical, chemical, environmental changes, but also morphological, anatomical, physiological, phenological, and or ethological responses in biota. So floodplain streams under the flood pulse regime present different hydrology throughout the year, in which they shift from lentic ecosystems during high water periods to lotic streams during low water periods. So this shift in their hydrology leads to unique ecological characteristics of floodplain streams in comparison to Amazonian upland streams where flood pulse influence is not observed. So, because of this influence of the flood pulse, the aim of this work is to answer how does the flood pulse influence the benthic community in an Amazonian floodplain stream? The study area is located in Porto Trombetas, a locality close to mining activities in the municipality of Oriximiná, Pará state in Brazil. It is located in the Trombetas floodplain basin in western Amazon, on the left margin of the Amazon River. The area is under the influence of the flood pulse regime, where four well-marked hydrological periods are observed. They are the low water from mid-December to mid-March, flood from mid-March to mid-June, high water from mid-June to mid-September, and drawdown from mid-September to mid-December. The study area is the Igarapé-Água Fria stream, which outlets into the Trombetas River around 1.5 kilometers upstream from the Trombetas harbor. In this area, we have the presence of traditional Quilombo community. As the area is under the influence of the flood pulse, it presents drastic changes of water level. During low water period, water depth is of 1.5 meters, as we can see in this image, but during high water period, mean water level can get to 7.2 meters. Because of environmental heterogeneity, water depth can range from 20 centimeters during low water to 9.1 meters during high water. During low water, the ecosystem is taken by macrophyte stands and the channel is moderately entrenched, where water flow is typical of lotic streams. On the other hand, during high water periods, the stream is flooded and presents no detectable water flow, becoming lentic. The adjacent riparian vegetation is inundated, as observed by the treetops in the video, and lateral exchanges promoted. We collected in 3 different sampling stations. They were considered representative of Igarapé-Água Fria environmental heterogeneity. Sampling stations are 500 meters distant between each other and stretch from 100 meters upstream the outlet up to 1.5 kilometers upstream from the outlet. Sampling was held yearly in 4 hydrological periods, from December 2014 to December 2020. In the field, water samples were collected in the subsurface and close to the bottom. We assessed water transparency, depth, temperature, and dissolved oxygen concentration in the water column. Also, sediment for organic matter analysis and benthic community assessment was collected with the Van Veen sampler with an area of 0.0408 square meters. Benthic community sampling was held in triplicate in each sampling station. In the laboratory, we determined the pH, conductivity, and turbidity from the collected water samples. Total nitrogen and total phosphorus concentration were also determined in the water samples. To identify the influence of the flood pulse on the benthic community structure, first we analyze the differences between ecological metrics in different hydrological periods. We calculated taxonomic abundance, richness, and channel diversity index, as well as the abundance for each functional feeding group using past statistical software version 4.03, where most statistical analyses were performed. Statistical differences between periods for each ecological metric were tested with one-way ANOVA and Tukey post-test when statistical assumptions were observed. If not, Kruskal-Wallis was applied. To identify differences in community taxonomic structure between hydrological periods, we performed a one-way Permanova analysis, and Simper test was applied through Bray-Curry similarity index. To identify which taxa contribute to differences between periods when differences were indeed observed, a canonical correlation analysis was applied to analyze relationship between environmental and biotic matrices, and linear and second-degree polynomial regressions were also performed to test correlation between variables. Taxonomic richness was significantly different between high and low water periods, according to Kruskal-Wallis test, as shown in the box plots. Taxonomic abundance was also significantly different between floating, high, and low water periods, according to Kruskal-Wallis test. The taxonomic diversity, measured through channel diversity index, was significantly different between floating and high water periods, according to one-way ANOVA and Tukey paired post-test, with p equals 0.03. These differences, although significant, were rather lower than those observed for abundance and richness metrics, where p-values were respectively equal to 0.008 and 0.02. Also, temporal trends show a pattern in the ecological metrics, but unexpected peaks in values might be observed. The graphs seem to indicate a fast increase in water level in 2017 floating period, which led to low taxonomic richness. On the other hand, the supposed fast decrease observed in 2019 drawdown did not influence the richness metric. Still, the intense increase in water level in 2017 floating led to low abundance, while the intense drawdown in 2019 promoted high abundance of individuals. Shannon Diversity Index presented stochastic behavior and was not influenced by water level. This phenomenon could be related to the coupling between sampling date and flood pulse moment. Traditionally, sampling is held according to the calendar window of each hydrological period, but sometimes the flood pulse is early or delayed for stochastic reasons, and the ecosystem might be environmentally more similar to the previous or next period than the one it actually is chronologically. Still, further studies are required to assess through hydrological mathematical modeling the gradient of the flood pulse level in function of time. The one-way Permanova indicated that community structure is significantly different between hydrological periods. When Simper test was applied through the Bray-Curry similarity index, it indicated that chironomid family represents 43% of the observed difference between periods, followed by cowborid family, responsible for 15% of this difference, while oligochaetes represent a little less than 15% of this contribution to differences between periods. These taxa are observed in every period and are the most abundant taxonomic groups in this stream. These groups present a set of adaptations allowing them to explore hypoxic ecosystems, so they thrive during high waters in comparison to other taxa. This must be the reason why they are so important, contributing to differences between periods, as shown in the CCA. As indicated in this box plot, significant differences in abundance are observed for chironomids and cowborids in every period, but between low water and flooding for cowborids. Still, the flood pulse did not influence abundance of oligochaetes. On the other hand, it is important to highlight that general benthic abundance was significantly lower during high waters, as you can see in the box plots. To identify the influence of the flood pulse on the functionality of the benthic compartment, we analyzed the relative abundance of each functional feeding group. The one-way Permanova indicated that community structure is significantly different between hydrological periods. Simper test was applied through the Bray-Curry similarity index, which indicated gatherer collectors are responsible for 63% of total differences between hydrological periods, while predators contributed to 31% of this difference. The presence and abundance of different functional feeding groups were sensibly different between hydrological periods. During low water period, gatherer-collectors are a majority. They represent 79% of the community, while the predators represent 28% of it. The flooding period behaves as a transitional phase between low and high water periods because predators' relative abundance tend to increase while gatherer-collectors tend to diminish until an inversion in proportion is observed during high water, when predators dominate the ecosystem, being 66% of the community, while the gatherer-collectors represent 32% of it. Still, we highlight that this inversion is rather explained by a decrease in gatherer-collectors' absolute abundance from low waters to high waters than an increase in predators' abundance between these periods, as it is clear in these box plots. Furthermore, it is important to note that some taxa are only observed during specific periods, while others are absent. Examples are oyster-colts, which are never present in high water period. Same is observed for many Ephemeroptera families as Leptocerid and Cnid, and for Coleopteras as observed for Eumid family. As a matter of fact, only 17 taxa were present during high water periods, but 11 are oligochaetes and 3 are in the Chironomid family. Thus, during high water period, the community is mainly composed by oligochaetes, Chalborid, and Chironomid, representing 88% of total abundance. On the other hand, low water periods are marked by the dominance of chironomids, nematodes, and other diptera, while Chalborid, some oligochaetes, and Smicrid and Trichoptera were absent. Still, much more other groups are present in comparison to high waters, even if in low abundance. This difference in richness was of 17 taxa present in high waters against 44 taxa present in low waters. To explain which environmental variables explained the changes in benthic community between hydrological periods, we performed the canonical correlation analysis, which evidenced that environmental variables explained 24% of the macroinvertebrate community composition. And the main variables explaining the variation in community composition were the bottom dissolved oxygen concentration negatively and the water depth positively on the horizontal axis. On the graph, we can observe that water depth values are inversely proportional to bottom dissolved oxygen concentrations. Black colored circles and squares represent high water and flooding periods respectively. White circles and squares represent drawdown and low water periods respectively. It is clear the influence of flood pulse level on the data distribution in the graph. Furthermore, when plotting the observed taxa correlated to the environmental variables, we can see many groups of oligochaetes associated to high water periods to the top right of the graph, while a diverse fauna is associated to low waters and drawdown on the lower right. To the top left, we can observe other taxa, mainly of shredders. Because of canonical correlation analysis, we performed linear regression analysis between ecological metrics and bottle dissolved oxygen. A significant correlation was observed between dissolved oxygen and abundance, but not between bottom dissolved oxygen and channel diversity index, as observed in the graphs. The low abundance of benthic macroinvertebrates observed during high waters is explained by dissolved oxygen, which is highly influenced by the depth, as indicated in this polynomial regression. Thus, bottom dissolved oxygen is the main limiting factor for the benthic community of Igarapé fria. Furthermore, the community structure and functionality are rather influenced by dissolved oxygen limitation than its diversity itself. Further studies on hydrological modeling of the flood pulse are needed to better understand its influence on aquatic communities. Further studies on hydrological modeling of the flood pulse are needed to better understand its influence on aquatic communities. Different functionality approaches other than functional feeding groups might be useful to better understand benthic community ecology in floodplain streams, such as physiological, anatomical, and ethological approaches. Also, further studies assessing spatial distribution influence on benthic community functionality should be held for a better understanding of floodplain streams benthic community. Thank you for watching. Leave a comment below or bring your questions and suggestions to our oral Q&A session. I am looking forward to meet you. These are our contacts and acknowledgements. See you soon.